I'll start for those that want to. If you want to continue by yourself, you're very welcome. Okay, so with these conjecture problems, I've just passed out a booklet, and I want to point out on the front of the booklet is a process. So with these questions, all right, there's easy marks at the start, and then they get harder the more you go through it. So we want to try and get the easy marks, complete the inductive cases. So when we look at this problem here, on the axes below, sketch the graph, clearly showing axes, intercepts, and the vertical asymptote. Now the first thing I want to tell you is, when you sketch this graph in your calculator, it gives you a V window. It says sketch from -6 to +6, and on the y-axis from -4 to +2. Then all you're doing is copying the graph. Now looking at it, we should know the roots. We can see the roots are x is 0 and the asymptote is x is -1. Okay, we can see that from the type of function it is. So we're going to sketch a asymptote at x is -1. So I'm going to sketch the function up here quickly, and you guys are going to draw that on your page. Now, don't rush graphs. In a test, in an exam, graphs are some of the easiest 3 marks that you can get. All right, so it's got this kind of shape here. Now, when I say that, what it means is there's 3 marks for the graph. So you're going to get a mark here for drawing the asymptote. You're going to get a mark for the axis intercepts. And then there's other features, right? For example, one of the features we should see is this local max. It's sort of going up and then it's doing this kind of thing here. So when we mark it, what we do is we say, is this local max roughly in the right position? How do you find the right position? Well, you can g-solve the coordinates of that max. Okay, it's x is 1.5. You can trace along it by pressing F1. If you press F1, it traces along the function. Okay, so you can determine those x values. And what we're doing when we mark it is basically we have a box, and might be in this circumstance, we're going to have a box, and your local max needs to appear in that box or on the edge of that box in order to achieve that mark. Otherwise, it's a too sloppy graph. Okay, so your graph should correspond with the actual values. All right, any questions about sketching the graph and how we allocate marks for it? Okay, so 3 marks there for drawing a graph from your calculators, copying. Part B, state the coordinates of the stationary point. All right, so the stationary point we know is a maximum or minimum. In this circumstance, it's a maximum. It occurs when x is 1. The y value is 0.5. Now it says coordinates, so that means we're going to state both. X is 1, y is 0.5. Alright, so our answer to part B, 1 and 0.5. The x value is 1, the y value is 0.5. Okay, now consider the function g of x equals 3x on top of x plus 1 squared. So it's a pretty similar function, except we're changing the number 2 to a number 3. Now state the x coordinate of the stationary point. Well, the stationary point now is x is 1, y is 0.75. Now these are what we call the inductive cases. They're inductive because you're building up particular pieces of evidence that lead to a general conclusion. So it's an inductive argument. All right, so we've answered part B, part C. Any questions so far? Just using our calculator, 5 marks there. All right, get those marks. Those are the easy marks. Remember, there's some marks that are easy, some are hard. We want to get the easy ones, and we want to get the hard ones. We just try our best to get those. So then we have the table, and they introduce us to this family of functions. So a family of functions means they're similar in some ways, but they're going to be different in others. So we have 3x, 4x and 5x. Okay, so we're going to sketch both of those. And here we've got the x coordinate and then the y coordinate of the stationary point. So for the first function, we have the x coordinate is 1, the y value 0.5. We have 1 and 0.75. Okay, so we're going to g solve for 4x. So So I'm going to change the function now from 3x to 4x. Okay, get that x value. We've got x is 1, y is 1. And then change it to 5. And we've got x is 1, y is 1.25. All right. So another mark there, just from G solving on our calculator again. So 6 marks all up. Okay. Any questions so far? Part E, make a conjecture about the x coordinates of the station, about the coordinates of the stationary point to the function h of x. All right, so they're introducing us to the general function. This function here, ax, on top of x plus 1 squared, that satisfies all of these, where a is a different number, right? So we're making a general claim about it. So we're saying, here we've got a is 2, here we've got a is 3, a is 4, a is 5. And we want some relationship between a and these numbers. So our conjecture, make a conjecture about the coordinates. So we've got 2 coordinates. We have an x coordinate. Seems the x coordinate is always 1. So we would guess our x value is going to be 1. And our y coordinate, it's tricky to see. I'm not going to say. If you think you know it, let's keep it to ourselves for now. Okay? We're trying to say, what's the relationship between this number here, 2 and 0.5, 3 and 0.75, 4 and 1, 5 and 1.25. There's a relationship between those numbers. Now, let's say we can't see the relationship. Doesn't matter. We can still go on and prove the conjecture and then come back and answer it. Let me show you exactly what I mean. And I'm sorry, we are going to go into lunch to do this proof, but we're going to do it now. All right? So, prove the conjecture you made. We can do it. This question here, if you're having a look again at the process, all right, what we've done, we've completed the inductive parts. Now, we should identify what type of conjecture it is. For calculus, there's 2 types, 2 main types. There are others, but the 2 main types are either tangents or normals and stationary points. This one's a stationary point, right? We've been finding stationary points. So what do we have to do for a stationary point question? Differentiate the function. Set the derivative to 0. Solve the critical points. So that's what we are going to try with this function h of x. We have h of x is ax on top of x plus 1 squared. Okay, what's the process? Refer to the process. Always the same. Let's try and get these marks. Differentiate it. That's easy enough. We know how to differentiate a function like this. That's the quotient rule. U dash. So u is ax, u dash will be a. V is x plus 1 squared. And v dash will be chain ruler 2 times x plus 1. Smash all that together to get h dash of x. U dash v, take away uv dash on top of v squared. All right, so that's the derivative function.
Down the bottom is e to the 4th power.
Good, it's x plus 1 squared. Thank you, Adam. Now, that's the derivative function. Stationary points occur, so we've done the first part, we've got a mark there at least. Stationary points occur when the derivative function equals 0. This is a reciprocal function, which means we don't even need to consider the denominator anymore. We're only interested in the numerator. We're solving this equation. We have a times x plus 1 squared, take away ax times 2 times x plus 1 equals 0. We're solving this equation. All right, that's when it's stationary. Stationary when the derivative function is 0, which means we're focusing on the numerator because it's a reciprocal function. Now, this popped up at the start of the lesson. X plus 1 is common. Let's pull that out the front. Which means we're left within brackets. A times x plus 1. Okay, that one there. And then we'll have take away to AX. All right, we are so close. We'll apply the null factor law. Here we get x is minus 1. That's our asymptote. So that's not a solution. Over here, AX, take away 2AX, gives us negative AX. So we have A take away AX. Yep, A is common. A times 1 take X. Apply the null factor law. A is not 0 because A is a number. So we have X equals 1. Now that's what we want. We want X is 1. We know the X value. We anticipated, our conjecture was, the X value is 1. We didn't have a Y value though. That's okay. Watch this. When X is 1, all right, the Y value is just H of 1. H of 1 is A times 1 divided by 1 plus 1 squared. That's A on top of 4. Look at this. In this circumstance, A is 2. 2 divided by 4, 0.5. Here, A is 3. 3 divided by 4, 0.75. Here, A is 4. 4 divided by 4, 1. 5 divided by 4, 1.25. So even though we couldn't see that pattern, or maybe you did, but even if you couldn't, we found when the X is 1, the Y value is A on 4. When X is 1, Y is A on 4. So then we can go back and fill that conjecture in, even if we can't see it.
You have to state that you have to reject.
No, we wouldn't generalize yet, but generally you would reject this solution because that's the asymptote. The asymptote occurs when X is minus 1. So really good, another conjecture problem there. So we've got a bit of work to do